Just a moment. Okay, great. All right, so I'm Danny Bolmash. I'm a postdoc at UMD, and I'll be chairing the next two talks. So our next speaker is Markus Greiner from Harvard, who perhaps needs no introduction. Markus, do you want to try sharing your screen and see if slides come up?
Let's see.
Perfect.
One
See
sec.
the slides.
Is the sorry, this is actually, but it's the wrong slide. Sorry, give me one.
Wrong slide, but otherwise.
You can, but it worked. It's okay. Sorry.
Yeah.
So does this work now?
Yes. Yes, everything looks good.
Perfect.
Yeah. So he'll tell us today about ultra-cold atom quantum simulations, exploring low-temperature Fermi-Hubbard phases. Go ahead, Markus.
Yeah. Oh, actually, yeah. I had there's a different title in the program, which is actually closer to what I will be talking about. Yes, hello everyone. So it's my great pleasure to tell you a bit about what can be done with ultra-cold fermions. It's quite special, I would say, to have fermionic particles natively, because that seems to be a really nice opportunity to realize models that are extremely difficult to compute or even impossible to compute, and where the computational where computations are very limited. And actually, at the very end, I want to get back to that. And if you're a theorist, also kind of I want to tickle your brain a little bit to. I think it's very interesting to try to understand why it's so difficult, and maybe to even understand these connections better. Why is it so difficult? Like, even if you had a full-blown quantum computer, how efficiently could you solve fermionic problems, and vice versa? If you actually simulate fermionic models for quantum simulation, or maybe even inspired by quantum computing, what kind of power do they give us, as opposed to like spin and boson models and so on? Well, I will be talking about quantum simulation because that's a really nice opportunity where we can really make a difference, like where we can do things in the lab today that are hard or impossible to compute. And I mean, this is naturally motivated. You know, we have atoms moving in optical lattices. You can see my cursor, right?
Yes.
Thank you. And so this, of course, is an analog to how electrons move in actual materials. Of course, we are not at the level where we, you know, program all details of an actual material. Instead, we really want to simulate fundamental, basic, simplified models, kind of, because even those are extremely hard to compute. So the whole research with fermions was started by David Jin, and but what I will be talking about is fermions in optical lattices, and you saw the talk already by Emmanuel Bloch, who gave a very nice introduction. So I will keep the introduction short and not motivate that anymore. So amazingly, if we have fermionic atoms in an optical lattice, they create a virtually perfect realization of this very simple model, like the most simple, non-trivial fermionic, strongly interacting model. It only has these two terms, right? The atoms can tunnel between neighboring lattice sites, and if you have there's Pauli blocking, so you cannot have two atoms in the same spin state on a site. There are two spin states, spin up and spin down. And if two atoms of different spin states are on the same side, then sorry, one sec. Good. Then that will cost the on-site interaction energy U. At high temperatures, you would expect metallic behavior for such a model, and then as you lower the temperature, the repulsion of the atom leads to a Mott insulator, where the population of doublons is energetically unfavorable, and so most of the time you will find one particle per site. There are, of course, excitations, whole doublon excitations, but to first order, you got one atom per site. Now, if you get even colder in temperature, then you get magnetism, you get interaction between the spins. It's actually interesting to ask why, right? Because the Hamiltonian I just showed you has no explicit spin dependence, or has no explicit spin-spin interaction. But what happens, of course, is that you have super exchange interaction, meaning that particles virtually tunnel to the neighboring lattice sites, but they can only do that if they're in opposite spin, right? If they're in the same spin, it's completely Pauli forbidden. If they're in opposite spins, they go there virtually. And so this ability to swap lowers the energy, and so antiferromagnetic, and that gives rise to an effective super exchange antiferromagnetic interaction if the interaction is repulsive. So yeah, really simple model, right? Amazingly, it's deceivingly simple, because while it's simple to write down, even until today, despite a lot of effort by many generations by now of theorists, there are many open questions. It's not really understood. What the kind of think we know is that it probably looks very similar, or its phase diagram looks very similar to the phase diagram of high temperature superconductors. And so Anderson already proposed it as a minimal model to understand materials such as high temperature superconductors, right? And
Markus, could I make a comment or ask a question?
Oh, please, yeah.
I hope you don't mind. I mean, the thing is that, of course, the Hubbard model phase diagram, we really know only for very large U or very small U, meaning right. Probably there is superconductivity in the Hubbard model, but I do not think that superconductivity is shown to have anything to do with high temperature superconductivity, meaning it's probably what I'll call Kohn-Luttinger type superconductivity, which in all fermionic interaction gives you superconductivity to weak coupling eventually at some low temperature in some high channel. So this DUF superconductivity that you have in your left panel, we should keep in mind may have nothing to do with the DUF superconductivity on the right channel, because you do not know if Hubbard model has superconductivity for moderate value of U or not. This is where you come in. You need to show us.
Exactly. So we need to try that. Exactly. Okay. And the nice thing is that, like, once we have that, we could really vary parameters. You know, it is relatively easy to, you know, add nearest neighbor interaction or vary the interaction strength.
All I'm saying right now, you do not know.
Exactly. Yeah.
Theory that the left-hand side, whether there is superconductivity or not.
Yes, yes, yes.
You have to tell us that someday. That's what I'm hoping. You'll tell us that someday.
Yes, we are working hard on it. So no, exactly. And I mean, to me, it's just amazing how a model that looks this simple can have this amount of complexity somehow intrinsically. And this ties into, you know, what does it mean to have fermions? What does it mean to have this sign problem that appears if you do quantum Monte Carlo? Right? Is that is there something even more fundamental behind this, or like, how do I understand this complexity? And even if I had a quantum computer, could I actually simulate this efficiently? And so questions like that. Okay, so right, and so we are trying to, or we are working on simulating that, and we have come pretty far. We're able to create antiferromagnets. So we have kind of like entered this phase diagram I just showed you into the antiferromagnetic phase, where we have antiferromagnetic correlations across the entire sample. As Emmanuel already showed you, we can sample from the many-body wave function by taking perfect snapshots, essentially. The easiest thing is to just image one spin state at a time. So for example, if you then have such a Néel-ordered state here, you see kind of a checkerboard appear. Or by now there are more and more experiments that can actually simultaneously measure spin and charge. But I should also mention that this is really a cartoon. Well, this is an actual measurement of a antiferromagnet in the Heisenberg regime. It looks nearly perfect, but that by itself is actually a bit deceiving, because you wouldn't expect a Heisenberg magnet to just look like simple Néel order. This is kind of a lucky shot, essentially, because in general, right, in a Heisenberg magnet, spin symmetry, and so only every once in a while, the direction of Néel order points into the z direction in which we measure, right? And so only then you get this kind of really high contrast images. And also, of course, it's a quantum magnet. So there are quantum fluctuations beyond the simple Néel order. But we were certainly excited when we saw pictures like that. We can do it more quantitatively. So we can measure, right, that we have strong antiferromagnetic correlations across the entire sample. Yeah, and so we call that antiferromagnet. Of course, it will always the order will always polynomially decay for such a magnet, and we can measure actually we can directly measure these decay constants. And as I said, keep in mind it's really a quantum magnet where you had a lot of additional correlation. If effectively the system takes a compromise between having local singlet states or a long-range Néel order. And this shows you how, as a function of temperature, right, this kind of this correlation length is diverging. Okay, so I showed you what happens if you go down here into the antiferromagnetic phase. But of course, in this regime, it is roughly described by the Heisenberg model, as we discussed earlier. But this is true if the interaction is very strong and you can neglect the whole doublet excitations. And that you can compute quite well. But it's actually, if you do quantum Monte Carlo yourself, it's kind of amazing to see like even quantum Monte Carlo of the Hubbard model on this axis works well. But then as we change the density a little bit, you can see how it immediately blows up. And it becomes really hard to understand what happens if you now put in holes, like if you have a magnet and holes present at the same time. And so that's where it becomes interesting. And so let's see what we can study with such a system. I will mostly focus today on work where we really look at the dynamics of individual holes in the system. And let me mention first there was a range of interesting experiments in quantum gas microscope which studied excitation, so either these long wavelength excitations with evidence for a bad metallic transport by Maissam Barkeshli group, for example, or DC spin conductivity, and but we can also directly look how particles or magnetic excitations move in a system, because we can use the quantum gas microscope to create these quantum particles essentially. In the simplest way, we just put a single atom into an otherwise empty lattice. That's what we did here. So if you put an atom on one lattice side and you let time evolve, you see that that the atom is doing a wonderfully coherent quantum walk. So this is actual data where you see how the atomic wave function expands, or how the wave function describing the position of the atom expands ballistically here. And you see this his famous quantum walk signature. And similar experiments have been done with magnetic excitation by Immanuel's group, right? You flip one spin and you see how the spin propagates. Now, what we can also do is we can go into the Hubbard model, like let's assume an undoped Hubbard model, but then we inject a single hole. And again, Immanuel has already shown this morning some interesting experiments along these lines, but let me tell you how we do it. In our case, we actually changing the potential on a single lattice side to keep the lattice side empty and build a magnet around that. And then we suddenly remove that potential, and now this atom can move. But let's just first consider one-dimensional system. So let's restrict the tunneling in the vertical direction and only have the atoms tunnel horizontally. And if we now let the hole go, you can see how it moves left or right. And after some time evolution, we take one snapshot, right? And we measure where the hole ended up. And if you plot that, we can see this nice quantum walk also. which is kind of, which in a way is kind of surprising, because what we have here is we essentially have a 1D Heisenberg antiferromagnet, and then we have this individual hole, but the hole actually seems to move completely freely as a quantum particle. And this is exactly consistent with what Immanuel explained this morning already, namely that we have spin-charge separation even in the ground state here, because essentially the hole doesn't care about the spin of the atoms and can move as a free quantum particle here and do this quantum walk. And likewise, the spins don't care about the hole, except if you want to see the magnetism here, you have to go into squeeze space where you take away all the empty lattice side and move it together, essentially. If you did a conventional kind of like magnetic measurement, you would not, you would, and if you had many holes, it would actually look random, and you would not see any kind of like longer range correlations. But if you go to the squeeze state, then you see that in the spin sector, the atoms just essentially form a Heisenberg magnet to first order. Okay, so that's in 1D, and it's quite simple. Spin-charge separation, and we can understand intuitively why that is. But let's go to 2D, because there it becomes much more interesting. And I think there's also, that kind of gives you a bit of a flavor for why these models, where you have antiferromagnetism on one hand, but also moving holes, like itinerant holes on the other hand, why they are so complex and also so difficult to compute. So what happens if I have a single hole here in such an antiferromagnet? Again, this is of course a cartoon picture. I said already, in reality we have something that looks more like a Heisenberg magnet and not just a simple Neal order. But what happens if this hole now moves? If the hole moves, it moves all the spins one side over, essentially. And that means that I can now trace the path that the hole took. So under these conditions, of course, the hole cannot just undergo a quantum walk, because now the path becomes distinguishable if you just look at the spin pattern. Right? In fact, that's what we see. It looks much more diffusive here, and I will get back to that in a bit. Well, this was already realized a long time ago, that you had these, or that this would happen if a hole moves to an antiferromagnet. But more recently, there were some interesting theory papers and prediction that one should maybe take that idea a bit more serious. And you can even cook up some effective theory, essentially, where you effectively have a spin-on and a hole-on that are bound by a string. So the hole-on is this new hole position here. The spin-on is, well, if you start out with a hole here, right, there's a missing spin. And so correspondingly, this is a spin-on of the, sorry, of the spin state. And in between, you have this string of atoms that are in the wrong spin state, right? And you may expect that there's some string tension. You may expect that this is, that you could maybe cook up an effective model. You may say, well, this string may decay, right? The magnet may repair itself, sure, but maybe that's within the model, right? What could happen is that the string splits open, and then you have a new spin-on string spin-on pair, so that's a magnon, and so spin-on string spin-on pair, and a new spin-on string hole-on, so that's your new meson, right? So maybe this is a good way to think about it, but it's not clear, because it's really not possible. I mean, the only calculations you can do are in a TJ model, and that's of course quite limiting. And if you have something like this, maybe, you know, like maybe this even gives us an idea on how things like superconductivity may emerge. Maybe it's as simple as, you know, you have a hole and a string and a hole. I don't think it's that simple. It may be more subtle kind of attraction, right? Or maybe the whole idea is wrong. But the point is, you cannot really compute to see if these ideas are correct or wrong, or if they are in fact misleading. So what do we do? Let's try experimentally how we can explore these ideas, or like motivated by these ideas, how we can explore what can we explore in the experiments. So in the experiment, what do we do? So we can first of all create systems in equilibrium as close to the ground state as possible. And then we take quantum snapshots. And I think this in itself is actually an interesting kind of aspect that we can really sample from the many-body wave function. Right? So in reality, you have a superposition of many different states, and we can really sample from that directly. We do this with many snapshots, like for example, for the data I will be showing you, we took about 30,000 samples, and and then we can take these snapshots and see what do we find in them. Typically, by the way, we only, as I mentioned earlier, we remove one state and only look at one. That was a bit limiting in the past, but as Emmanuel showed already this morning, there are ways to circumvent that and then really image everything at the same time. And we are also about to have that implemented. So if you have these snapshots, right, what can you do? The first thing is you can look at a traditional, like, two-point correlation function, for example. Spin and hole correlators, or also like, magnetic order, or the likelihood to find two holes to each other, next to each other. And this is very related to the kind of observables you have in condensed matter physics, for example. But you can also do much more than that, because you have a complete snapshot. And that means you can look at, for example, high order correlation functions. So, and recently in the context of many-body localization, for example, we were able to see that that is really an amazingly powerful tool. Like, we could see in many-body localization, we could really see the logarithmic entanglement growth by looking at these high-order correlation functions and things like that. Or we even go beyond that and actually look like pattern, with some kind of pattern finding algorithms, or also with machine learning. We have some papers on that too in the Fermi-Hubbard model. So what kind of pattern can we find? Well, motivated by this theory idea earlier that I said, where a hole would leave this kind of string behind, we thought, well, wouldn't it be nice to actually look at this kind of string pattern? Do we find any evidence that this kind of thing is happening, that more often than randomly, we find these kind of zones where a hole has moved through and has left this kind of string of atoms that is now in the wrong spin state? I said already, we need many shots to do that. But once we do that, we can then compare it to different theories, right? So one possible theory we could compare it to is, say, well, let's say the holes just appear sprinkled, or and there's no connection really between motion and holes and the magnetic states. Or we could take some kind of theory where we say, okay, how about maybe the state I have starts with, or would initially look like an undoped magnet, but if I now put in holes, I have to take into account that those holes move around. And so if I start with an undoped magnet, I could maybe I could move the holes in a way to create these strings artificially, corresponding to some string length distribution that I find from a TJ model. So this was proposed here in this paper. Or I compared with completely different theories that have nothing to do with strings, but I can still, I can still use these theories, for example, pi flux theory, to create samples that I can then analyze in exactly the same way as the experimental data, and see how good of an agreement that gives me. And in fact, all the data we took is actually online on GitHub, so everyone can actually take the data and also look for, their favorite theory, or because the raw data is available, you can really look at what you can apply to different models. But let's look at the strings. So what we find here is, so this is how many strings of a certain length we find, and at half filling we wouldn't expect any strings. So this is kind of, sorry, at half filling we don't expect any strings. So this is just a baseline essentially, because as I said, the state is not a simple nil state. So our string finding algorithm then finds all kind of fake strings essentially. But if we actually go to the doped regime, we find significantly more. So this is a factor of a few more of these objects. So that's quite interesting. And so we can then compare it to theory. Again, the sprinkled holes, that would not agree with the what we find for the doped regime. But if you then take a theory like the simulated strings I mentioned, then we find pretty good agreement. And at higher temperatures, for example, indeed, we see that there's no change. We can also measure how many strings we have as a function of doping here, and we can subtract what we actually find at zero doping here. So this essentially we subtract, or we take this as a baseline here, what we find at zero doping. And then again, we can compare to different theories like sprinkled holes, our string theory, and so we see pretty nice agreement. But of course, you can also compare to other theories, like the rotating valence bond theory, for example, also looks quite good. So in any case, we got some evidence that maybe this isn't a completely stupid idea. Maybe in some, at least in some regimes, this may actually be a nice picture emerging. And so what we wanted to do next then is to really see if we can create a single hole on demand and follow its evolution, and see how does it move in such a magnet, and how does it affect the magnetism, and how is the magnetism also affected by the hole moving away again. If you see changes in the magnet, do they heal again? Things like that. The tools we use for making these holes, but also for example, encasing atoms in a box or so, use a spatial light modulator where we can apply additional light pattern onto the atoms. And we already used that actually to create the antiferromagnet that I showed you earlier, because we can do some entropy engineering by having a big halo of a dilute metal, as shown here. The entropy actually goes into that, a lot of the entropy goes into that halo, and we get a cold center where we then find the antiferromagnetic order. But we can use the same setup also to just plug a single lattice site, meaning we slightly raise the energy of the lattice site such that the site becomes empty, but the surrounding lattice sites are not affected. Okay, and we can do either one hole, or if we just look at shorter time evolution, we can even have multiple holes at the same time. We then prepare the magnet around that, then we plug the hole and see how the atom is moving. Also note the systems are quite long here, right? Because we do want to really track the travel of the hole over quite long distances here. And note that for these large sites, any calculations are really pretty much impossible. What you can compute for the actual Hubbard model is mostly exact diagonalization. Right, so then you're really limited to something like 12 sites, but of course that would be a tiny region, so that's not very usable. Otherwise, you have to do things like TJ model, where you neglect double hole excitations, and then you can do DMRG, for example, where you can have somewhat bigger systems, but even then, a typical system size is maybe 4 by 12 or 4 by 16 sites, and the small dimension here also big. So and the small dimension where you only have 4 sites already becomes quite limiting, for example. Okay, so what happens if you now put a hole and let it go in the Hubbard model? We start out with a hole at position 0 here, and so we plot its distance. We mirror, because of signal to noise, it takes a long time to take this data. We mirror it once across X and Y to get the a better data quality, and we made sure that it's symmetric overall. And so we see that the hole moves away from the original site. How does it look compared to a quantum walk? So for short time evolution, we find pretty much the same evolution, like for half a tunneling time. But after that, we see a strong deviation from what you would expect from just the tunneling of a single particle. And of course, that's exactly what you would expect. Because what happens is, if the tunnel, in a quantum walk, if the particle, for example, tunnels from its original site to another site that's off by one diagonally, you have multiple paths that interfere, that lead to that final place. And so if you had a polarized background, right, then you would really have a situation where you have, like, if all the atoms are just spin up, then these two paths would really interfere, and that would give you a probability to find the particle there corresponding to this quantum walk calculation. But we don't really expect that, because we have atoms in two spin states, and if the atoms are in a different spin state, then you can actually see in the pattern afterwards which path the atom took, and hence you would not have that interference. So that means if, for example, we take a random spin background, then sometimes you have situations where you have interference, and sometimes you have situations where you don't have interference, because the spin gives away the information which path the hole took. And so that would, with that, you would expect a decrease. So this is random background in a quantum Monte Carlo calculation. But if you actually start with an antiferromagnet, then pretty much each time you can tell which way the hole took, and so that should be further reduced, and that's in fact closest to what we observe experimentally. We can also look how the hole moves away. So we fit the distribution with the Gauss, which seemed a fairly good, we confirmed to be a good model for this. And what we find is that at short times, like up to one tunneling time, the motion of the hole, so this is the RMS distance, how far the hole has traveled versus the time. So for short times, we find that it moves ballistically as you would expect for quantum walk, but that's essentially this very first step where it would tunnel to the neighboring lattice side and maybe slightly beyond. So there you have this ballistic kind of motion as you know it from the quantum walk. But if you go beyond that, then it looks, and I mentioned already why, it looks very different. We can actually compare it to a nice model, where you assume, so in the extreme case, you would assume that all the paths are, that you can distinguish all the different paths, and that gives rise to a beta lattice model. And so essentially, if you start on one side, right, that every single path is distinguishable, and you go down this fractal graph essentially to the final location. And what's nice is that such a model already tells you about this crossover from the initial ballistic motion to a more diffusive motion. And so if you plot, if you compare it with the beta lattice, then we see a comparison like this. So again, initially ballistic, and then it's not that far away from such a beta lattice, but it is lower. So this seems to be not the whole story, the beta lattice. The spread is a bit slower. Why is that? And so, well, what you would expect is that the whole, it shouldn't just go. So in this beta theory, you would completely neglect the magnetic effect, like J equals 0 essentially, right? But what you would actually expect to happen is that the whole interacts with a magnet, right? And this would happen on the timescale of J of the spin spin-spin interaction. And so in order to study that, we repeated the same experiment at two different values of the ratio of the tunneling and the interaction energy, U of t, which affects the J, right? So in these two data sets, J varies by about a factor of 2 here. And in fact, we see that the local slope is also varying by about a factor of 2 here. So that gives you an indication that we actually have polaronic physics going on, where the movement of the hole is really determined by the magnetism around it, essentially. Let's look at the magnet to see if that makes sense, or like what do we find if we look at the magnet, the magnetic correlations, depending on how the hole is moving. So here we are plotting the magnetism around the initial hole, and specifically we plot the correlation between the lattice side where we had the hole initially and the other surrounding sides. So for t equals 0, we don't have an atom there, or we shouldn't have one there, so there shouldn't be correlation. And so this is only effectively noise because we have a little bit of an amplitude to still have an atom there. But if the hole now moves, then we see quite quickly that we get an interesting effect where so the brown color is actually correlation the wrong way. So we don't get antiferromagnetic correlation, but we get them with the wrong sign because the atom, because what happens is the hole has moved to here. See, and now this one here has the opposite correlation from the staggered magnetization here. So this is exactly the opposite of what you would find if this atom was red here. And after a long time, when the hole really has moved away, then we see these positive correlations again, this positive antiferromagnetic correlation. But what's also interesting is that for short distances here, we always have the positive correlations. Okay, we can plot the strength of this correlation here, and so as a function of versus time logarithmically plotted here, we see that initially, this is now the correlation on the diagonal side, and so initially this has the wrong sign, and then it relaxes to the right sign. But over many tunneling times, we also find that it does not reach the equilibrium value, which would suggest that the hole really deposits its energy into these magnetic excitations, for example. Can we make sense of this quantitatively by assuming some effective model again, as I said earlier, motivated by this kind of string picture? We can actually build a model where we have another kind of beta lattice where we can take the string tension into account, like proportional to the length of the string. We now have a string tension, and we have the spin-on-hole-on model. And if we compute, or this was done by Fabian Guss and Annabelle if you compute that, let me go forward. I think this animation is slightly messed up. You can compute that and take snapshots essentially. So again, this is not a full theory. This is just a simple kind of calculation of this effective model. But if you do that, you find a pretty nice agreement. So this is the simple beta theory from earlier, where we don't expect any magnetic interaction. And then here is a theory based on this effective model. Yeah. Okay, maybe skip this. So this is more data where, as a function of time, you see how the magnetic correlations recover again. So this is for short time. This is at 0 time as a function of distance, and plotted is the nearest neighbor correlation here, and you see how this is also like over time this spreads out, and this is also pretty nicely described by this model. So that's suggestive that this is at least not completely wrong. So maybe this is a good, it may actually be a good way to think of this. Yeah, so it's quite exciting to really play with this, or with these models in a regime where it's, like you can't really compute what is happening, but we can kind of start to test models like this. And maybe, like if you have indication that such an effective model is good, maybe you can even arrive at a point where you can study either computationally or in the experiment, where you could see if this gives rise to like a D-wave Cooper pair, for example, right? What you could imagine is that if you think about it as an effective model of these spinons, holons, and strings or so, would you expect this to prefer holes to be close to each other, to be coupled? And in fact, in the experiment, we would be planning to then have 2 holes at the same time. And then we could study, are they moving independent of each other, or are they moving collectively? Is it more likely to find them than close to each other? Before doing that, we want to lower the temperatures a bit, and also it's important to implement the spin and charge imaging at the same time. But if we have that, this would be quite possible to do experiments like that. It's of course not easy, because we also have to deal with the fact that in such a big system, a single hole is not a very easy target, because we have a lot of background holes. There are, for example, so we are not in the infinite mod limit, right? There are also whole double-on excitations, but we can actually quench those excitations out quite a bit by quickly adiabatically kind of increasing the interaction strength, and then those disappear, and we only see these holes and thermal holes if we have some, but we should be cold enough to not to worry about that. And then once you're a bit colder, we can also really see what kind of other emerging phases do we get, and how can I understand that in this context? And so yes, so it's really exciting to study this very intricate interplay between the spin and charge degrees of freedom. As I said, we want to get colder. A few years ago, we already created this mod insulator, which has much lower, this bent insulator, which has much lower entropy than we currently have in the antiferromagnetic phase. So this entropy redistribution scheme works quite nicely, that we showed that where we put entropy into a halo. But of course, it works even better if the center is a gap phase. So if we actually make a band insulator, we can do this ridiculously well, corresponding to a very low entropy per particle. But then the art would be to then isolate that from the rest, which we have already shown in the past, but then to also transfer it adiabatically into the state of interest, which is then not just the simple gap state, but other states like a doped Hubbard model. And of course, this ties into questions, like how adiabatic can you be and everything. In any case, we certainly want to try that. One nice scheme is where you turn a single lattice side of a band insulator into a double well, as proposed here, and as we have already tried once. for very small systems, but in a system that was technically very limited. And what you would then get is that you would turn your singlet on a single side into a singlet on a double well, and if you connect those, then that should be adiabatically connected to a ground state, certainly in the undoped case. And then in the doped case, things are probably even more subtle, and one has to see how adiabatic one can be. But we also have a lot of other ideas involving reservoir engineering in all kind of different ways. And so we are currently actually making a major upgrade of the experiment where we implement a lot of techniques that we can use to try to get even colder and also to image spin and charge at the same time. And so one of the things we are currently implementing is what Thomas Esslinger's group has already in their potassium experiment. So Daniel Greif, the previous postdoc, started that, and we are currently finishing this. And this is like an interfering lattice where we can then make a lot of different lattice potential, starting from an array of double wells, but also things like, for example, a honeycomb lattice or a triangular lattice or things like that. So, which of course will also be very exciting if you can go beyond a square lattice where a lot of physics is expected to happen in a lot of interesting regimes. Here, for example, you would have some spin frustration right away. So it's really an exciting time to be able to do simulations today in the lab of quantum systems that are extremely hard or impossible to compute. And with the quantum glass microscope, we can take these kind of snapshots and patterns, and we have some evidence for this Polaron dynamics, which is quite intriguing. I would like to end just by thinking about it in a slightly bigger picture, because I'm really curious also what are connections between quantum computing and our Fermi Hubbard simulation. Like what you see in the NIST quantum computing is that oftentimes, you have spin models that map onto optimization problems, that map onto all kind of different problems, as the previous speaker showed, for example. The question is, what do we bring to the table having fermions? We know that the fermionic models are extremely hard to compute. But what does that mean? Is that even fundamental and so on? And if you had a quantum computer, could we actually efficiently simulate that, right? In principle, you can with the Jordan-Wigner transform, but the problem is that the Jordan-Wigner transform turns this kind of local fermion model into a highly non-local model. For a full-blown quantum computer, you may say, well, that doesn't matter. But I think that any kind of quantum device will actually benefit a lot from locality, right? Because after all, local space, like real space, is defined by the space in which interactions happen locally. So the question is, my question is, can we turn this around maybe? We have an experimental system that is local, and if we build experimental system, we want local interactions. We have a system that is local, which maps onto a highly non-local spin or qubit system. And can we maybe turn this around? Could there be useful models somehow that cannot be easily solved, that are like non-local spin models connecting to interesting problems, but they maybe map to local fermion models that we can realize in the lab? So I just want to put that out as a thought. With that, I would like to thank all the students and postdocs who did the experiments. So the experiments were led by Martin, Lebras, Jeffrey, Christy Chu did the previous experiments that I showed in the beginning, and Muxing and Lev and Anand, they are currently preparing the big upgrade of the experiment. Good, thank you very much.
Great, thank you very much for an excellent talk. So let's open the floor up to questions.
Markus, this is Bill Phillips.
Hey, Bill.
Good to see you virtually.
Yes. Good to see you.
Thinking back to Emmanuel's talk and the result that showed the different transport between the charge and the spin, what I'm wondering is, does your picture with the strings allow that feature to be explained or to emerge?
In 1D, you mean?
Well, I'm not sure.
So yes, I mean, this is really compatible with that, right? And in 1D, we see the same spin charge separation. And then in 2D, where he has the, okay, that's an excellent question. I don't know. And right, and I hadn't also seen some of those results yet. So, I mean, his main result that he showed in the end, there was quite a different regime, I think, where, yeah, where it's not really doped. And so kind of like that's Heisenberg dynamics, right? So that is a bit simpler. But for the other things, it should apply, yeah.
Yeah, so what I'm wondering is, how does it look? That is, if I've got this string and there's some tension in the string, does the whole move along and then sort of drag the spin behind it, following the
exactly
path?
So how I think about it, and again, you know, this it may still turn out that the model isn't so great or is only good in certain regimes or so, but the idea would be the whole moves around, and to a certain extent it is bound to that spinon with the string, right? And so and in fact, what we see is that the holes, like initially they move with T, then later with J, so which would be compatible with the spinon being dragged around essentially. But of course, the string can also break, right? So then it would break into a new meson and a magnon. But maybe I can think about it, you know, like in high energy theory, that these processes can happen both ways, and depending on the temperature, you have either you can also have a lot of thermal magnons. Or at lower temperatures, then everything becomes more quantum mechanical, and you have these coherent processes. So the picture is certainly intriguing, and everything we saw so far is consistent with the picture. But
and yeah. Do you think that things would change very much if you went to the kinds of superlattices that you were showing, or the things that like Trey Porto did before, where you don't have a square lattice, you have this more complex thing that you can change? Do you think that string picture would still apply?
I mean, certainly not for a system with spin frustration, for example, right? It would still apply for situations where the tunneling is different, for example, different dimensions. In fact, that would be an interesting thing to study. Because then you would expect strings to be more aligned with a certain direction, because that would minimize, you know.
Yeah.
If you study like a 1D 2D crossover, for example, that would be interesting. Yeah, and then I would be really curious to see if a string picture could explain things like the pair formation, right?
Yeah.
Like, does it give and I mean, we certainly just want to do that experimentally, you know. Do holes move? Do they move independent of each other or in a correlated fashion? And what kind of magnetism do I find around those two holes then? And can I explain it that way?
Yeah. And whether you can distinguish, say, polaron physics from string physics.
Right. I mean, in a way, this kind of string is just an interesting kind of polaron, right? You can just view it as an interesting kind of polaron.
Okay.
And then those strings interacting with one another would then, would then be polaron interaction essentially. Yeah.
Yeah. Okay. Thanks.
I mean, let's see. I don't know. And if some theorist in the audience has a better idea of some other kind of pictures we should test, I'm all for it.
Markus, I had a question, which is a high-level question. So you have this Hubbard model simulator, almost ideal, not completely ideal because you can't really go to zero temperature and so on, but
Right.
let's not worry about those things, okay?
Mhm.
Because you can certainly go to lower temperature than what quantum Monte Carlo can go. So what are the facts that have emerged from your own work? One thing that's clear to me, you have definitely seen antiferromagnetic correlations. Is that a correct statement? There is no doubt that you see antiferromagnetism.
Sure.
in the,
Right. Like you can see a long range, what we define as
range,
long range
not just
antiferromagnetic, meaning over the entire system.
right,
Yes.
right. You see, okay, that's
certainly
for
right.
sure.
Mhm.
That's a definitely positive advance. Okay. Now, can you put some limit on the value of interaction that is needed to see it? Meaning, do you see it for all values of u? You can tune your system to?
Yeah. So in the first paper, we tuned some of those regimes. I mean, currently, again, the temperature is such that we want to be not too far away from the optimal U. But in that regime, you know, we have studied like for an undoped system. Actually, we have done very detailed comparison with theory.
Yes.
And then we in fact see that to first order it's Heisenberg, right? But we also see deviation from Heisenberg already because we are not in the we're not anymore in a regime where you can exactly distinguish. Sorry, where you can neglect whole doublon pairs, and then then we are in a regime undoped. We are in a regime where you can then do still an actual Fermi-Hubbard calculation, and that agreed very nicely.
Good. All right. So now the second and third quick questions. I just want to know what are the empirical facts you have discovered. Okay.
Right. And then we measured as we go away.
Right.
And started doping how the order disappears.
That was the next question I was going to ask. For very low doping, and of course Eugene knows all about it, and I know you talk a lot with Eugene. Do you see any sign of ferromagnetism at all, like like Nagaoka ferromagnetism, or is that regime not? You cannot explore.
We are not currently in that regime. Yeah, we could put ourselves in that regime, but that's not something we have done yet.
You neither have seen it, but you don't rule it out either. It's not like
no. It's not that we have looked and didn't find it.
You cannot rule it out because it's an exact result, but you needed one hole to see the exact result. And the third question, which is a question everybody has, so far you do not see any direct sign of superconductivity. There may be some indirect, right?
Right, certainly not. And I mean, I would expect to be a factor of, I don't know, of a few to high in temperature, obviously, right?
Okay.
But even if we are colder, right, it's a non-trivial problem. How would we then even see it? We thought we're thinking about things like a Josephson oscillation or so, right, in bulk, with the bulk S-wave superfluid, for example, in Florence, right? They did nice experiments where Josephson, for example, shows you actual oscillation.
This is a very good point. So what you're saying, not seeing it doesn't mean it doesn't exist because you have not explored it yet. Because it's not clear how to explore it, and your
right. I mean, I don't expect it at our current temperature, but who knows? It could be there. And
yeah, no, I get it now. Your temperature.
Right.
All right, that's very good. Thank you. Thank you very much.
Right.
Thank you, Marcus. Very good talk.
All right, and I think that brings us about to the end of our time for this segment. So let's thank Marcus again for an excellent talk.
Thank you.
And now. Maissam, are you here and ready to screen share?
Hey, Danny. Yeah, I'm here. Can you hear me?
Yeah, we can hear you. Let's see. Do you want to test your screen share first?
Yeah, just give me a second.
Great.
So can you see that?
You can see that.
You said you can see it?
And yeah, I can see it, but it doesn't look like presentation mode at the moment. It, can see the, there we go. That looks great. All right. So our next speaker will be Maissam Barkeshli from University of Maryland, from CMTC, and he'll be talking about measurement-induced topological entanglement transitions in random quantum circuits.
Okay, thanks, Danny, for the introduction, and thanks to Shankar for the invitation and for organizing this, and to all the other organizers. So I'm going to be talking about a pair of works that we posted over the last year with Ali Lavasani, who's my graduate student at UMD, he's a JQI fellow, and Yahya Alavirad, who was a student at UMD with Jay Sao, and has now since moved to UC San Diego, where he's a postdoc with the Simons Ultra Quantum Matter collaboration. So this talk is about random quantum circuits. So the basic point about a random quantum circuit is that you have some collection of qubits. Usually we're interested in these qubits being on some lattice. And at each time step, we're going to apply a randomly chosen set of unitary gates or measurements to some collection of the qubits. So for example, we'll be interested in applying 2-qubit unitary gates or some measurements on a few collection of qubits at a time. So a typical kind of architecture might look like this figure on the right. So these random quantum circuits have become very interesting over the past few years and have been the subject of a lot of intense study. And the reason is because they're useful for a number of things. They're useful for solvable models of quantum dynamics. So if you want to study information scrambling, growth of entanglements, there are even connections to black hole dynamics. It's very useful to gain insights from these random circuits. And so this paper by Nahum et al. From 2017 is one of the early papers in this subject. But of course, there have been many papers since then. And there's also important connections to quantum complexity. So Google's famous quantum supremacy experiment, for example, was about sampling the output of a random circuit. And this has been mathematically rigorously shown to be computationally difficult classically. So it's a way of demonstrating that quantum computers can do something that classical computers cannot. So actually, this subject kind of goes back even before many of these papers, because early on, quantum information theorists were interested in how you can approximate just random unitaries in the unitary group, specifically Haar random unitaries. And they were interested in approximating these Haar random unitaries over some large number of qubits in terms of random unitaries on some small number of qubits, like 2 or 3 qubits or whatever. So that's kind of where this subject maybe originally came from, as far as I understand. Now, more recently, several groups have discovered that these random quantum circuits, when you add measurements to the problem, actually exhibit a very interesting kind of phase transition that was completely missed before. And this phase transition is an entanglement phase transition. So let me describe what this means. So as an example, let's consider qubits, a 1D array of qubits. And we're going to consider a circuit architecture that looks like this figure on the right. So at each time step, we're going to apply 2-qubit unitaries. That's these blue boxes. And these are going to be random 2-qubit unitaries. And we can decide that we're going to pick Haar random unitaries from all possible unitary transformations on 2 qubits, or we can decide that we're just going to randomly pick 2-qubit Clifford operations. The Clifford operations are useful because those you can classically simulate numerically. So you can really try to understand what's going on in the circuit at large system sizes. So at each time step, we apply these random 2-qubit unitaries. And then in between the time steps, we consider the possibility of adding some single qubit measurement in the Z basis with some probability P. Okay. So the entanglement transition is, as you vary this probability for these single qubit measurements, as you increase this P from 0, there's a phase transition at a critical probability. And that phase transition is exhibited in the entanglement entropy of a subregion, averaged over all quantum trajectories of this random circuit. So you kind of, you run this random circuit and you keep track of the specific state that you get after every time step, after every unitary measurement. So it gives you a trajectory, and then you just average over all of these trajectories. And this transition, you can think of in many different ways. One way is it's a transition between a state which has volume law entanglement entropy and area law entanglement entropy. The area law phase is like a disentangling phase. It's like if you put enough of these single qubit measurements in, then that kind of disrupts the entanglement growth that's created by these random unitaries, and doesn't allow you to build up entanglement over long scales. So it gives rise to this area law entanglement. Whereas if you have very small measurement probability, then you can build up this entanglement and you get this volume law entangled phase. And the phase transition here is critical, so as we'll discuss. Now, the interesting thing about this transition is it's not visible just from standard expectation values. So if you just track the mixed density matrix that you get by applying these measurements, and you look at expectation values, the expectation values are completely insensitive to the value of P at late times. So you really have to look at something kind of non-linear in the density matrix, like the entanglement entropy averaged over these quantum trajectories, in order to see something here. Now, perhaps the surprising thing here is that you might think that the moment you add some amount of measurements here, you will eventually disentangle the phase. And so you might think that there should be no stable volume law phase the moment you add some single qubit measurement probability. But it turns out that that's not the case. And basically what's going on here is that if you imagine starting from a pure product state, this random unitary dynamics is creating a highly entangled state. And these measurements, even if you have some finite rate of these measurements, you can't fully reveal what the state is. So you can't kind of completely disentangle the state using some small amount of measurements. And a couple of years ago, it was understood then that you can think of this volume law phase as a kind of quantum error correcting code, where these local measurements just give you some local information about the system, but not enough information to completely destroy the entanglement. Now, important conceptual insight came from Michael Gullins, who's here at NIST, and David Hughes, where they kind of recast this entanglement transition into what is called a purification transition. So here you imagine, instead of you start off with the system in some pure state, and then you look at what the entanglement entropy is, whether it's volume law or area law, you start off the system in a maximally mixed state. And then you ask how quickly the measurements purify the system so that the entropy of this mixed state goes to 0. So if you have a high measurement rate, then you have a purifying phase where it takes basically order 1 time, independent of system size, to take the entropy to 0. Whereas if you have low measurement rate, then it takes exponentially long time in system size to purify the state. So basically, this is another way of looking at the fact that there are states whose distinction is completely hidden to local operators. And so that's the connection to quantum error correction. So the phase which takes exponentially long time to purify is the phase where you have low measurement rate, so you can't kind of efficiently distinguish between the different states in this maximally mixed state. And so it takes you exponentially long time to purify the state. So this exponentially long time to purify the state, that phase is the volume law phase over here in terms of entanglement, whereas the purifying phase is the disentangling phase, area law phase. Now, another important aspect of this entanglement transition is that it's described by a conformal field theory, at least in this simple example of a 1D system with 2-qubit unitaries and single qubit measurements. So now there's a number of things that you can think about in order to, well, there's a number of situations that you can consider. First, you can consider that the random unitary, the unitaries are Haar random over like in the space of unitaries acting on 2 qubits. So for Haar random circuits, what you can do is you can map the calculation of the entanglement entropy to a statistical mechanics model using replicas. And what these authors showed is that in the limit where the qubit dimension is infinite, this entanglement transition maps directly to a 2D classical percolation problem in this statistical mechanics model. And then finite qubit dimension, you can think of as kind of a relevant operator at this 2D percolation fixed point, which triggers an RG flow to some different conformal field theory. And that conformal field theory, it's unknown what its properties are. Now, instead of considering Haar random unitaries, you can consider random Clifford unitaries. In this case, you can efficiently numerically simulate it, so you can extract a lot of accurate information about the critical exponents and so on. In this case, people looked at this particular example quite carefully, and they found that the critical exponents, like the correlation length exponent or the dynamical exponent, are the same as 2D percolation, but there are other universal quantities, like the coefficient of the entanglement entropy at the critical point, which does not match what you would expect from a 2D percolation model. So this has led people to think that there's some kind of conformal field theory here that we have not identified, which describes the transition in these Clifford circuits. So this is, you might call it some unknown Clifford conformal field theory. And furthermore, one of the original papers in this subject looked at the zeroth Renier entropy, and they just showed the zeroth Renier entropy, by the way, is it's basically the number of non-zero eigenvalues in the reduced density matrix. So there's an entanglement transition that's also visible in the zeroth Renier entropy, and that transition can be mapped to percolation, to 2D percolation. However, the entanglement transition and the higher Renier entropies, in particular the von Neumann entropy, has different properties, different exponents, and so on. So it cannot be mapped to percolation. Now, when so far we've discussed kind of this volume law to area law transition, but from our experience in studying quantum phases of matter, we know that quantum many-body states which have area law entanglement actually have a very rich classification. So there's a rich classification that involves symmetry, topology, the algebra of operators, and the way to describe the different possible quantum phases of matter uses a lot of sophisticated mathematical structure: group theory, cohomology, cobordism theory, higher category theory, and so on. And these are subjects that I and many others are even studying to this day to try to understand the full scope of quantum phases of matter in equilibrium. So here you can similarly then ask what class of many-body phases can be stabilized via these random quantum circuits, and how would we probe their distinctions beyond just area law versus volume law entanglement entropy, or via this kind of vanilla purification dynamics that I described a few slides ago, where you just ask, does it purify or does it not purify? So in the past year, there's been a lot of interesting papers on this subject. So here I just mentioned a few. What I'll be talking about is our paper, which is, well, our set of two papers, which is mainly focused on topological entanglement. There was another interesting work by Tim Shea and his students, where they looked at a circuit with Ising symmetry, and they saw some kind of spin glass type order, among other things. There's interesting work by Ehud Altman's group where they noticed that you can actually think of the kind of replica symmetry of the ensemble of circuits as part of the important symmetry specification of the circuits, which lead to different kinds of phases. And then these authors last year also found that you can have universal subleading corrections to volume law entanglements. But so far, I don't think anyone's shown that you can have different volume law phases which have different subleading corrections according to what was found in this paper, but I might be wrong. So you can ask not only what class of phases can we stabilize via these random quantum circuits, you can also ask what kind of critical points can we stabilize, right? So far, what I mentioned about critical points was that everything's very closely related to percolation. So indeed, there's this 2D percolation that you can get. There's this unknown Clifford CFT, which seems to be very closely related to percolation. Andy Lucas and Xiao Chen and Jason Iaconis showed that you can get directed percolation. Just very recently, there was a paper by Norm Yao and Altman and others at Berkeley, where they showed you can get continuously variable exponents if you include long-range interactions. So what I'm going to be describing in this talk is
Maissam, a quick question, because I'm completely ignorant. Is this quantum percolation or is this classical percolation? Because
this is classical percolation.
But everything about classical percolation is known. Mathematicians have worked everything out. Right? There's nothing open, right?
That's right. So what I'm saying is that certain critical points in these random quantum circuits can be mapped to classical percolation. And when that happens, we know everything about it.
Really? I mean, that sounds very mysterious. I mean, because this is classical percolation, no tunneling, right? Just
right, classical percolation.
Wow.
So actually, I will describe to you a few scenarios in which we have an analytic mapping to 2D percolation.
Okay, good. Yeah, I look forward to that because this sounds magical to me. All right, go on.
But I think the interesting thing is that not only can we get classical percolation, we also get these kinds of critical points that we have never seen before. So one of them is this Clifford CFT, which seems strange, but also I'm going to show you another one that shows up in one of our models where we get some very strange behavior, and I'll tell you about it.
Maybe it will become clear, but is that part of this classical percolation mapping, or is this something that is different? I mean, that's what I'm not.
No. So 2D classical percolation is different from this Clifford CFT and from this log violation of area law and so on that I'm going to tell you.
Good. So that doesn't automatically follow from percolation. This is some additional physics.
Correct.
Okay.
In fact, percolation, will not give you this. Yeah.
Okay, now I feel better. All right, thank you. Mm-hmm.
Okay, so I think the broader thing here that's interesting is, in condensed matter, one of the things that we're interested in is studying different phases of matter. Well, random circuits provide a new paradigm for studying interesting phase diagrams. So what we're used to is we have some Hamiltonian, it's a sum of local terms. We tune some parameters, lambda, and we look at a phase diagram as a function of lambda. But now we have a whole new set of things that we can do. We can instead consider measuring HA with different measurement probabilities, and then we can add some random unitary dynamics to the mix, and then we can consider a phase diagram where we're varying these different measurement probabilities. So in the simplest case, suppose that we consider a Hamiltonian, which is a sum of two kinds of Hamiltonians, where each kind of Hamiltonian itself is just a sum of commuting operators. There's A operators for H0 and B operators for H1. So what we can do is we can consider a random circuit where we have different probabilities for measuring A type operators or B type operators, in addition to the random unitary dynamics. And we can study what kinds of interesting phase diagrams that we can get. So I should mention that basically right after we posted our paper, there was another two papers that appeared by these two groups, which kind of consider a similar problem. And there was an earlier paper by Skinner and Nahum, which do something similar, although for Majorana zero modes, but without adding any random unitary dynamics. Okay, so what we'll be interested in is we'll pick H0 and H1 to stabilize distinct quantum phases of matter, like different topological phases of matter. And then we'll try to study non-trivial order parameters to distinguish the phases beyond just looking at volume law versus area law. So the first thing that we'll do is we'll study a 1+1D model where the 1+1D Hamiltonian stabilizes a symmetry-protected topological state, SPT, which has a global Z2 cross Z2 symmetry. So specifically, we'll consider an open chain with n qubits. N is going to be even. The Hamiltonian is just XZX on 3 neighboring sites. These operators all commute with each other. And then there's a global Z2 symmetry. If I take the product of Z operators on the even sublattice, and then the product of Z operators on the odd sublattice, these 2 operators commute with the Hamiltonian. So I get a Z2 cross Z2 symmetry. Now the eigenstates of H0, which have the same eigenvalues of G1 and G2, have the following properties. First of all, they can all be related to each other by a constant depth local unitary circuit, which preserves this symmetry. They cannot be related to just a trivial product state by a constant depth local unitary circuit, which preserves the symmetry. However, they can be related to a product state by a symmetry breaking constant depth local unitary circuit. So this is this is basically the statement that it's a SPT. SPT means that it's trivial in the absence of symmetry, but is non-trivial in the presence of symmetry. Although the fact that every eigenstate of H0 can be related to each other by this symmetry preserving constant depth local circuit is more about the fact that this is a commuting Hamiltonian, which is just has these Pauli operators, so it's quite simple. So the order parameters that we'll look at here will be a kind of topological entanglement entropy, where you look at the this particular combination of subregion entanglement entropies. So this combination, it turns out, will give you 2 for an SPT state, but 0 for a product state. So it's a kind of order parameter that can distinguish these 2 topological phases. And another order parameter that we'll look at, I don't think I'll give you show you our data for it in this talk, but we did look at this one as well. This is a kind of string order parameter where this string is basically just a product of these XZX operators from point I to point J. And the reason you're getting Y's here is just because there's a Z and then an X that comes up in that product. So this is just a string of these stabilizers. And in the SPT state, this expectation value is ±1, and then it's 0 for the product state. So what we're going to do is we're going to square this, and then we're going to average it over the system. So the fact that we square it here means that this is no longer a simple expectation value, right? It's like taking an expectation value and then squaring it. So it's kind of, it's like non-linear in this way. And this is going to be important because if it was just a simple expectation value, there's no way that we would be able to see an interesting phase diagram. So this random circuit, the way it looks is that at each updating step with probability PU, we're going to apply a random 3-qubit Clifford unitary, which preserves the Z2 cross Z2 symmetry. And we're just going to pick one. So we're going to pick I, the particular qubit, center qubit. We're going to pick that uniformly at random. And then once we pick that, we're going to apply this 3-qubit Clifford unitary with probability PU. Then with probability PS, we're going to apply a single qubit measurement ZI with I selected uniformly at random. And then with probability PT, which is 1 minus PS minus PU, we're going to apply this 3-qubit stabilizer measurement, again, with I selected uniformly at random. So at every updating step, we're only applying one gate, unitary gate, or one measurement to the entire system. So because of this, one time step is going to be n updating steps. So that one time step is kind of extensive. We have something that acts on the whole system, whereas each updating step just has something that acts on, 1 or 3 qubits. So we could instead consider a layered circuit architecture like this, but and we also did that, but here I'm just going to present this particular one. So some limiting cases here is obviously if the single qubit measurement probability is 1, then we're just going to get a trivial product state at late times, no matter what we start with. If the 3 qubit stabilizer measurement probability is 1, then at late times we'll get the SPT. And then when the unitary probability is 1, then we'll just get a volume loss state at late times. It'll just be some highly entangled state. So we have a few analytical results, and then I'm going to show you numerical results for this. The analytical results first, the first interesting thing about this is that there's a duality map. So there's a unitary operator, the duality map, which takes x to x, it takes z to this xzx stabilizer, and then takes the xzx stabilizer back to z. So this duality is essentially mapping the ensemble of random circuits at probability PS and PU is 0 to the ensemble at 1 minus PS and PU is 0, because it's just interchanging the single qubit Z measurement with the stabilizer. And this duality map, it doesn't completely keep invariant the entanglement entropy of a subregion, because it can kind of lengthen an operator from acting on 1 qubit to acting on 3 qubits. But it keeps the entanglement entropy invariant up to just some constant. So if you have an area loss state, you're going to get mapped to an area loss state, and similarly for volume law. This duality then implies if there's a single critical point, it must occur at PS equals 1/2. The next analytical result is if you just study the steady state density matrix, it becomes maximally mixed. So specifically, let's fix a specific realization of this quantum circuit and view the measurements as quantum channels that give a mixed state density matrix. So we're not keeping track of a single quantum trajectory, we're just keeping track of the mixed state density matrix as we apply these measurements and unitaries. So this circuit Q is just some quantum channel, which takes our initial density matrix to a final mixed density matrix. So if we start off with this pure state, we get some mixed states. And what you can prove is that if you start with some ensemble, if Q is chosen from an ensemble where these probabilities are between 0 and 1, PU is less than 1, then you can show that with probability 1 at infinite time, you're going to get to completely maximally mixed states. Here, these are projectors onto the +1 eigenspace of the symmetry operators, but that's it. Within this subspace, they just look like the identity. So this thing just becomes completely maximally mixed within this particular eigenstate of the symmetry eigenspace of the symmetry operators. So this means that if you, and then the expected time to reach this steady state is order 1 if the unitary probability is 0, and it's order n if the probability for the unitary is greater than 0. So this just proves that if you were going to look at naive expectation values, you would never see anything, because you would always just evolve to a maximally mixed state. To see anything interesting, you're going to have to do something kind of nonlinear in the density matrix. Right, so that's exactly what I just said. So the third analytical result is that there's an exact mapping to 2D percolation when you have no unitary dynamics. And it's a kind of unconventional classical percolation problem that you get mapped to. So to see this, what we do is we break the qubits up into those that are on the even sites and those that are on the odd sites. If Zi is not measured at step M, then we draw a vertical link between the I at time m-1 and I at time m. If xzx is measured at step M, Then we draw a horizontal link between I-1 and I+1. And then we assign a single color to all qubits that are in a connected cluster. So just to show you what that looks like, just to illustrate that, suppose that you start with, these are qubits on, say, the even sublattice. So we, in this diagram, we would apply a Z, if Z is not measured, we apply this, we draw a vertical link here. The vertical link means Z is not measured. And then if XZX is measured, we draw a horizontal link. So here we have a horizontal link where we measured XZX. And then the next step, the fact that there's no line here means that we measured a Z. So this guy got cut off from what was there before. And so now this gets its own unique color. So at the end, we have qubits that there's a unique color for each connected cluster like this. And the basic point is that if you want to know the entanglement entropy at a given step, then all you need to know is the assignments of colors at that step. And the idea is essentially that qubits of the same color essentially form their own kind of SPT states. So you have these kind of, the clusters means that you've broken up the system into a bunch of kind of independent SPT states. So it's also kind of nice, one thing that helps give some intuition for how you can build up a lot of entanglement just through measurements without any unitary operators is the following graphical representation of the state, again at 0 unitary dynamics. So imagine you start with a product state. So the product state is stabilized by just these Z operators. Then at step M, the stabilizer set is going for the state, looks like some string of Z operators on the odd sublattice, a string of Z operators on the even sublattice, and then this kind of this string operator also on the odd sublattice, where here you have X and then a string of Z's and then an X, and similarly for the even sublattice. So it turns out that at any given step, your state is going to be an eigenstate of these operators for some choices of J and K. So graphically what you can do is you can draw a blue line. Okay, the picture's over here. So you would draw a blue line above that connects I and J for every Zij stabilizer. And then we draw a red line below that connects I and J for every Gij stabilizer. And we treat even and odd sites separately. So basically, if we start here with a product state, then we just have these blue lines connecting the qubit to itself because it's stabilized by a single Z operator. And then we apply this XZX measurement. So then what that does is that now the state is stabilized by this XZX. So we have a red line going under, and then it changes the other stabilizer so that now it's a Z string going from here to here. And so you can just kind of track the state graphically in this kind of way. So you can see visually that as you apply these stabilizer measurements and Z measurements, there's the possibility for getting these lines that connect qubits that are very far away. And basically the entanglement entropy of a given region is directly related to the number of lines that are crossing the boundary of that region. So you can see that you can get some entanglement buildup. So there's a possibility for having, what's going to happen is we're going to get logarithmic entanglement entropy, or like the entanglement entropy of a region is going to grow like the log of that of the size of the region at the phase transition point. And so this kind of gives you a picture for how you might build up that a large entanglement that could give rise to a logarithm, as opposed to just constant entanglement. So the phase diagram ultimately looks like this. You tune the single qubit Z measurement PS. you tune P, the random unitary, and you get stable SP. There's a robust SPT phase, there's a robust trivial disentangling area law phase, and then there's a volume law phase. And there's a tricritical point over here where all three of them meet. And we have two critical lines that are coming out of the tricritical point. And ultimately, these critical lines end on this line over here, which is the volume law to area law transition that was originally studied a couple years ago by Matthew Fisher et al., by Adam Nahum et al., and so on. So this kind of gives a broader phase diagram that in some particular limit gives you that original entanglement phase transition. Now this PU equals 0 line, that was the line that I mentioned earlier, that I described how it can map to a classical percolation problem. Remember that we treated the even and odd sites separately. So we actually get 2 copies of a classical percolation model. So this tricritical point at PU equals 0 is, you can think of as percolation squared. The conformal field theory that describes this is like 2 copies of percolation. Yeah, I think this is like kind of a minor technical comments. This transition is percolation, but it's an SPT to trivial transition. It's actually unrelated to the SPT to trivial transition that occurs in equilibrium at 0 temperature if you were to just tune the Hamiltonians from the SPT Hamiltonian to the trivial Hamiltonian. So this random circuit transition is giving a transition between these 2 phases that's distinct from the transition that you would get in equilibrium.
Maissam, quick question.
Yeah.
So you're averaging over an ensemble of the dynamics, but in terms of starting states, is this true for an average of different starting states, or in some sense, or is this what would happen at late times for any symmetric starting state or initial state?
You can, so actually, I guess I'll describe it more soon when I get to the ancilla order parameter, but it doesn't matter what you start off with, essentially. You can start off with any state you like, or you can start off with like a maximally mixed state even. You're going to get this phase diagram. But the question is going to be exactly how you probe it. So let me tell you, I'm going to show you some plots for exactly what we calculate.
Okay, thanks.
I also have a question on this slide since we're here.
Yeah.
So in the absence of the unitaries and when PS is less than 1/2,
yep,
those stabilizers, the ZXs, they're basically Hadamard transformed versions of the usual cluster state stabilizers, right?
I don't know what basis people usually discuss the cluster model in. So
usually you have ZXZ. So
okay,
for each side there's an X with sandwich, sandwiched by 2 Z's. So if you just did Hadamards, it seems like you would have that set. And so I'm wondering, without the extra unitaries, are you basically projecting towards a cluster state? Yeah,
this SPT state is a cluster state.
It is, okay. And that's true for any PS up to 1/2?
Sorry. I mean, when I say it's an SPT, I mean, you have to be careful here. When I say SPT, we have this ensemble of circuits, and then we're looking at properties where we average over quantum trajectories. So when I say it's an SPT, what I really mean is, well, you'll see the next slide, but what I really mean is, for example, when we look at that order parameter, the topological entanglement entropy, when we look at this topological entanglement entropy order parameter, this thing will be 2 everywhere in that phase. So that's the sense in which I'm saying it's an SPT phase. There's this kind of topological order parameter, which is the same everywhere. But I wouldn't say that, I mean, because it's an ensemble of states,
right, yeah,
then I wouldn't use the words that you said. I would just kind of mention it in terms of average order parameter.
Thanks.
Okay, so here are some numerical plots. We tune the transition PS. We look at the topological entanglement entropy. It shows this really nice transition and these are different system sizes. So if you do some scaling collapse, where you pick the correlation exponent 4/3, which is what you have for 2D classical percolation, you get an absolutely beautiful collapse over here. This transition requires the Z2 cross Z2 symmetry. If you break the Z2 cross Z2 symmetry by, for example, doing single qubit measurements in the X basis instead, the transition just goes away. If you look at the entanglement, if you go to the critical point and you look at the entanglement entropy of a subregion, then that looks like what you'd expect for a CFT, where you have this log L. You can fit it to the usual form of a CFT entanglement entropy. And then the coefficient here is a universal quantity. It's not related to the central charge. It's actually related to some kind of boundary condition changing operator, because here we're looking at the entanglement entropy of a state, which is occurring at the boundary of this 2D circuit. So anyway, the interpretation of these coefficients are different from what you would normally expect, but they're universal nonetheless. And then you can look at the time dynamics, and you get that matches this formula. And then the AT and the AX are the same. So that's evidence for the fact that the dynamical scaling exponent is 1. Now there's another order parameter, which you can use this, an order parameter that was proposed by Gullins and Hughes, which we call the ancilla order parameter, to detect the purification transition. So here the idea is you start with a maximally mixed state, and then you study how that state is purified by the measurements. Now what we'll do is we'll introduce a bunch of ancilla qubits, and then we'll create a maximally mixed state between the, maximally entangled state between the ancilla qubits and the system qubits. And then we'll look at the entanglement entropy of the ancilla. Okay. So in the trivial area law phase, the entanglement entropy goes to 0 in time that's constant. In the volume law phase, it goes to 0 in a time that's exponential in system size. So we did two different things. One thing that we did was we ran the circuit for time 2n, and then we entangled a single ancilla qubit to the middle of the chain. And then we ran the circuit for an extra n time steps, and we measured the entanglement entropy of the ancilla. This turned out to not give anything interesting. What you really need to do is do this scrambled ancilla order parameter, where you introduce many ancilla qubits, and then you run a non-symmetric random scrambling circuit, like involving totally random 3-qubit Cliffords, which are non-local, for a bunch of time steps, 10 time steps. That was just kind of arbitrary number. And then we run the circuit to measure, and then we measure this ancilla entanglement entropy. So basically the point is you need to make sure that you start off with a sufficiently scrambled state between these two guys, the system and ancilla, and you also need to make sure that you've kind of populated states in every symmetry sector of the theory. So you need to make sure that the scrambling circuit that initially scrambles it does not obey the Z2 cross Z2 symmetry. So now the ancilla order parameter, particularly the scrambled one, shows a beautiful transition where the entropy, this is now again 0 unitaries. So we have a transition between the ancilla entropy being 2 at late times to being 0 at late times. So that's the SPT to trivial transition. And then if you turn on some unitary dynamics, what you'll find is that this ancilla, the scrambled ancilla entropy is 2, then it shoots up, becomes very large. The maximum it can become is 10, so because we only have 10 ancillas, but that's the signature of the volume law phase, because you don't purify and the entanglement entropy stays maximal for exponential time and system size. And then finally, when you hit the trivial phase, it goes down to 0. So this plot is of the same thing, but for the topological entanglement entropy. And the middle one is for this unscrambled ancilla, which cannot distinguish the two different, the topological and the trivial phases. And the reason is because the point is that the scrambled ancilla order parameter is saturating to log base 2 of 4. And this is related to the fact that you have 0 modes on each edge for the SPT. So the one of the characteristic properties of the SPT is that you have 0 modes at the edge of the system. So you have 2 states on the left edge, 2 states on the right edge. And that shows up here as the fact that you have basically 2 logical qubits, and the ancilla order parameter is entangled with these 2 logical qubits. And these local measurements cannot disrupt this entanglement because the logical qubits, the distinction between them is non-local. I think one point I'd like to make is this purification transition and the entanglement transition. When I introduced it as kind of 2 sides of the same coin, but it turns out that they're not exactly the same. You can have a situation where you have no purification transition, but you do have an entanglement transition. Basically, if you consider this system and you take periodic boundary conditions, then there's no residual degeneracy because you have no edge states. So this ancilla entropy will be 0 in both the SPT phase and the trivial phase. So it cannot distinguish them. However, there will still be an SPT to trivial transition that you can diagnose. And you can diagnose it by looking at the string order parameter, for example, that I had introduced earlier. So that is still non-zero even with periodic boundary conditions, but the ancilla order parameter will be 0 on both sides and will only show the critical points if you have periodic boundary conditions. So lastly, let me discuss, in this 1+1D model, let me discuss the critical properties along this critical line. Now it turns out everywhere along this critical line, the correlation length exponent and the dynamical exponent are all consistent with being 4/3 and 1. So, which is what we had for percolation. However, if you try to estimate these coefficients here, AX and AT, for the entanglement entropy, which I had said were also universal, then these things vary along this whole curve. So it's not quite clear what's going on here. One possibility is that the values that we extract for AX and AT are close to their value in the thermodynamic limit. In this case, it means that there's a whole marginal line of CFTs all connected to each other by marginal operators. And then this CFT over here is the Clifford CFT, and this one is percolation squared. So you'd expect that there's some kind of marginal operator here that takes you continuously from one to the other. However, it seems that there's no marginal operator in percolation squared, at least to the extent that I've understood percolation. So this possibility seems like it's probably not true. There's another possibility, therefore, that once we turn on this random unitary, that triggers RG flow to this Clifford circuit over here. And there's some weakly relevant operator. So these values that we're seeing over here along this line have not yet reached the thermodynamic limit, but rather there's some intermediate values in some kind of crossover region. So we don't know really what's going on here. Okay, so those were our 1+1D results. Now let me discuss 2+1D, try to get through it more quickly. So here, what we're going to do is we're going to go to 2+1D. We're going to add toric code stabilizer measurements. We're going to add single qubit measurements, and again, random unitary dynamics. So there's 2 classes of circuits that we look at. One is a measurement-only circuit, where we have a competition between toric code stabilizers and single qubit measurements in the Z or Y basis. So here, the idea is we'll have L squared qubits on a torus, periodic boundary conditions. The qubits are on vertices of an L by L square lattice. We have 3 sets of operators. We have the toric code stabilizer operators, which are going to be all X's or all Z's, depending on whether we're on the even or odd sublattice. Then we have single qubit Z's and single qubit Y's. And basically at each step of the circuit, we either measure the toric code stabilizer, the single qubit Z, or the single qubit Y with probability PZ, PY, or 1 minus PZ minus PY. There's another circuit where we look at only single qubit Z measurements, not single qubit Y measurements, but then we add random Clifford unitaries into the mix. So this is going to be random 4-qubit Clifford unitaries that compete with toric code stabilizers and single qubit Z stabilizers. Okay, so again, the circuit is very similar to before. And now our order parameters are going to be the topological entanglement entropy for 2D topological phases. That's is very famous, averaged over all the quantum trajectories. And that's going to be 0 in the trivial area law phase. It's going to be 1 in the topological phase. And then it's going to be something that grows with system size in the volume law phase. And then the other one is this ancilla order parameter, which is essentially the same as what I just described in the 1 + 1D case. So I won't go into that. And then the third thing that we'll look at is the entanglement entropy of a cylindrical subregion on the torus. This particular thing is interesting to look at, we'll see. And what we expect is when we're at a 2 + 1D critical point, we expect area law scaling for the entanglement entropy. So what's going to be interesting is the subleading term of this cylindrical entanglement entropy. So it turns out there's 2 distinct forms that show up depending on where we are in the phase diagram. One form that shows up looks like this. It's basically like quasi 1D. So it's some constant plus, some constant plus a logarithmic piece over here. And then there's another form that actually fits most of the critical lines along the phase diagram, which takes this form, where J is this combination of Jacobi theta functions and Dedekind eta functions. And this, I never saw this form before actually until Ali and Yahya showed it to me. But it turns out that this is a known result for some 2 + 1D critical points, like a scalar boson with exponent 2, so-called quantum Lifshitz model, and also some holographic conformal field theories. Their cylindrical subregion entanglement entropy fits this form. And I don't think anyone really knows why, actually, and also how common it is. So again, this is the point about purification transition is not quite the same as the entanglement transition, but I'll skip that because I already said that. So here's what our phase diagram looks like in the measurement only circuit. So here we have a competition between single qubit Z, single qubit Y, and then the toric code stabilizers. So the green is the toric code phase. Yellow is a volume law phase. This is interesting because this is a volume law phase that shows up in a measurement only circuit. Just that you have these competing measurements and they compete enough and generate enough entanglement just through their competition that you can get volume law entanglement without any random unitary dynamics whatsoever. And then everything else is the trivial phase. Now, this phase diagram is interesting along the x-axis and the y-axis. So the axis where pz = 0, so this axis along of py, this one has a self-duality that maps py to 1 - py, which is why it looks symmetric about py = 1/2. And then the py = 0, it turns out that here there's an analytic mapping to 3D percolation. So this critical point here on the pz axis maps analytically to a 3D percolation problem. So because I'm running out of time, I won't explain this duality, but this is the self-duality that I was mentioning. These are the plots for the entanglement, the topological entanglement entropy, and the ancilla entropy. So there's a robust topological phase where this thing saturates to 1. The ancilla saturates to 2 because we have 2 logical qubits in the toric code phase. And so we have the single critical point. This is the py axis at pz = 0. Okay, so it was the vertical axis in the figure that I just showed. The most interesting thing here, which I'll just basically spend my time explaining this and skip over the rest, is that the phenomenology of this critical point is quite new and very surprising, and we don't really know what to make of it. So what's happening here, this is the critical point at pz = 0 and py = 0.5. So we fit the topological entanglement entropy to this scaling form. The thing that's unusual here is this L to the gamma. This is an anomalous exponent for the entanglement entropy, topological entanglement entropy. This is something I've never seen before, an anomalous exponent for topological entanglement entropy. The SA does not have this because we have only 10 ancillas, so the ancilla entropy is limited, so we wouldn't be able to see an L to the gamma unless we made the number of ancillas grows with system size. So we get some correlation length exponent that we can't identify. We get a dynamical exponent which indicates anisotropy between space and time. So this is not a CFT. And furthermore, we have this anomalous exponent for the topological entanglement entropy, which is 1. This is the first time I've ever seen a non-trivial anomalous exponent here. So this is some weird unknown critical point. Furthermore, if you look at the entanglement entropy for a cylindrical subregion, it matches this quasi 1D form. And furthermore, this coefficient A, if you look at this fit, is linear in the length of the torus, L. So this actually means that we have L log L contribution to the entanglement entropy. So we have a logarithmic violation of the area law. So we have a very weird critical point. This critical point is log violation of the area law as anomalous exponent for this topological entanglement entropy and has anisotropic space versus time scaling. Now, we don't really know why this is happening and what exactly the origin is. Probably the origin is somehow related to the fact that you have a subsystem symmetry. If you take a product of Y operators along any horizontal or vertical loop, this is a symmetry of the circuit. So the circuit has actually 2L symmetries associated with these these string operators. Now, so this smells like this should be related to the fact that you have this log violation, quasi 1D form, and anomalous exponents over here, but it's something we still don't. We haven't been able to nail that down, and the reason is because even when we break this subsystem symmetry by replacing Y measurements with Z measurements along some diagonal, these properties all persist. So maybe there's some kind of emergent subsystem symmetry even when we break it explicitly. I don't really know. So now let's add a small PZ. We add a small PZ.
2 minutes.
Sorry?
You have about 2 minutes left.
Oh, 2 minutes. Okay, yeah, I'll just wrap up. If we add a small PZ, these lines open up. This is actually a tricritical point. We have volume law phase. And basically all along this critical line, the exponents match 3D percolation. So this point we could map exactly to 3D percolation, and everything else, the exponents match 3D percolation, except this one point over here. And furthermore, the entanglement entropy everywhere else follows this quantum Lifshitz type form instead of the quasi 1D form. And the log L violation goes away everywhere along this line, except at this tricritical point. Okay, so I was going to explain this mapping to 3D percolation, but I don't have time. So yeah, it's similar to the 1D mapping to percolation, where you can just pick some colors, and depending on whether you measure certain toric code stabilizers or single qubit measure stabilizers, you add vertical links, and then you make sure that everything in a certain cluster has the same color. And then you can prove that the color labels completely determine the entanglement of the states. So that's basically the idea. Yeah, so let me just summarize the measurement only circuit. We have at PZ equals 0, we have this exotic tricritical point. At PY equals 0, we have an exact mapping to percolation. We have these robust topological, trivial, and area law phases. And then everywhere away from this tricritical point, the critical exponents match 3D percolation, although some of the quantities which you'd think are universal, like various coefficients of entanglement entropies, do vary along that transition, similarly to the 1+1D case. Okay, so there's also 2+1D circuit that we studied where you add random unitaries as well. And the only new thing that shows up there is it seems like there's some signatures of a whole critical phase, not just the critical points. But of course, critical phases are extremely difficult to nail down in finite size numerics. So I'll just end there. So I'll just end with an outlook. Basically, the question is, what kinds of phases and phase transitions can we realize in these circuits? It seems like a huge playground of seeing all kinds of interesting things. Thank you.
All right, thank you, Maissam, for an excellent talk. I think we are going to have to cut off questions for now because we have to move to the next speaker, but thank you. And I will turn it over to the next chair, Youngjit.